Hello, welcome to lecture 27. So for this lecture, we're going to design and analyze the steel truss in our sample model. Okay, so the first thing that we need to do here is to set up the different load cases or load combinations. So we already have the primary loads for dead load, live load, and wind load. Okay, so the next step is to add an auto load combination. So for the load combination, let's use NSCP 2015. And for the category, you can use ASD or LRFD. But for this sample, I'll use ASD. Then click Generate Loads, click Add and Close. After that, let's proceed with analysis. So we already have the perform analysis. Next is to define the load list. So under Post Analysis Commands, click Define Commands. Then under Load List, select the load combination for ASD, click the right arrow sign and click Add. Okay, so this is now the load list. Next is to go to the Design tab. So the same thing that we did in concrete, click the material. So this is for steel. And for steel, we can use AISC 360-10. Then next is to define the different parameters. Okay, so for the defined parameters, this is quite different because you need to include the method. So you can use ASD. Since we use the ASD load combination for the method, we have to use also ASD. Okay, so click Add. Next is the FYLD. So FYLD is the yield strength of steel. So that is 248. Okay, click Add. So also we can check the ratio. So this is the permissible ratio of actual load to section capacity. Okay, so normally that is 1. Then click Add. So greater than 1 is considered as fail. Okay. Also, we have to check the or include track. So again, let's use track 2 for the printing of design output at maximum level. Okay, then click Add. Then for the commands, so let's click the check code, then click Add. Okay, so here we can assign it to view because these are all steel. So assign to view, ratio also assign to view, track 2, and check code. Okay, so let's run the analysis and check if you have any error. Okay, so we don't have any error, warnings, or notes. Let's proceed with the view output file, click Done. So under output file, we can, at the end of this, so we can see here the design part. So say for example, L2024, this is member 1. So as we can see, this is pass. So this is the slenderness ratio, allowable slenderness ratio. Then these are the design forces, section properties, and so on. Okay, so you can also check if you have any failed members. So find and replace, then find, say fail, then click next. Okay, so we have one failed member. So that is member 2. The ratio is 1.66. So let's check member 2. So member 2 is located here. If we double click it, then go to design property or still design. So this is the design part where you can see the critical load, the FX or the axial for tension, and MZ. Okay, so as you can see here, the tension is, this is the demand and the capacity is 180. So this is okay. But as you can see, our MZ, the demand for MZ is 1.8, but in actual, the capacity is just 1.2. Okay, so that's why this member failed. Okay, so if you have any failed member, you can just assign a bigger section for that column. But also you can check the different loads. So in post-processing, select ASD, then click apply and OK. Okay, so again, we can check the different load diagrams for dead load, roof live, wind load Z, positive Z, and wind load negative Z. Then you can check the displacement. So this is now the displacement, displaced figure for wind, for dead load, for roof life, for WL positive Z, WL negative Z. Okay. Also, under utilization ratio, okay, so these are now the ratio for each beams. Okay, so here we have a ratio of 1.67. So this is also failed with MZ. Okay, so the top bars are failed, and then we have some failed members here at the bottom bars. Okay, so let's proceed. Next is the utilization ratio. So these are the utilization ratio. As you can see, all the top members are failed. So you can also check the loading diagram for Fx or the axial, Fy, Fz, Mx, My, and for Mz. Okay. For the layouts, you can check the displacement, the reaction. So these are the reaction for truss, then the beam forces, beam stresses. Okay, so you can check the beam stresses at different levels and graph. Okay, so you can also check the MZ, Fy, and axial Fx for each members. Okay, so let's go back to the analytical modeling and the design. Okay, so here under parameter 1, before we proceed with ratio, so click FYLD for 248,000, then click define parameters. So let's just add some design parameters and let's see if it will pass. So beam, let's add first UNT. Okay, so UNT stands supported length for top flange for calculation of bending capacity. So for UNT, as we all know, we have purlins for the top chord. So let's just check the spacing of the purlins. So in the structural plans, we have, so this is for the roof framing plan. Okay, so where is the purlins? Okay, so purlins has an spacing of 0.5 meters. So going back to our plans, let's define parameters and UNT, that is zero point 0.5 for the spacing of the purlins. So here, click add after current, because if you don't check the after current, it will add a different parameter. So for UNT, select the top chords, then assign to selected beams. Okay. For the FY or LYLZ, so LZ is as is 1. For FY, so let's check. See, this is 5.368, 9.5. Okay, so let's check first. Run analysis. Click done. Then under post processing, let's check the utilization ratio. Okay, so envelope. So still the same. So I think we need to increase the section. So to do that, under modeling, analytical modeling, properties, then let's increase the section for top chord. So section database, for angles. So this is 2024. Let's check 2025. Then LD spacing is 0.06 or 0.1. Add. Then click the section number 3. Select the top chords. Then click assign to selected beams. Okay, then click again the run analysis and save. Okay, so done. Then let's check again the post-processing. Select the AST, click apply, and OK. So let's check again the utilization ratio. As you can see, the utilization ratio for the top chord decreases. Okay, so let's increase again the property. Okay, so 6. Let's use 25 by 3. Change. Let's use it also for the bottom chords. Click assign to selected beams and yes. Okay, so we forgot to click LD and the spacing. 0.01, 25, 3, change. Okay, so click analysis and design, then run analysis. Okay, so again, in post-processing, select the ASD load combinations, click apply and OK. Then check the utilization ratio. So still failed. Okay, so let's try again to increase the thickness. 25, 25, 5. LD 0.01, change. Then run. Okay, so let's check again the utilization ratio. So as you can see now, all the members are, or all the members pass because the ratio here is less than 1. Okay, so the highest ratio for the bottom, for the top chord is 0.872. So we can optimize this design, but for now this is okay. Okay, so you can change the sections and check the utilization ratio. As long as your ratio is less than 1, it is considered pass. But if your utilization ratio is greater than 1, it will automatically be red. Okay, and it means that your member failed. Okay, so if we double click the member, then check the still design. Okay, so as you can see here, the result is pass, and this is the ratio. This is critical for this equation, and this is the slenderness ratio. Okay, okay, so that's it for still design and investigation. Thank you.